In a formal system architecture, performance optimization and operational survival are defined over different mathematical structures. The optimization objective is computed as an expectation over the ensemble of all possible system trajectories. Survival is a property of individual trajectories. A trajectory either remains within the feasible set for the required duration or it does not. These two structures are not equivalent and do not imply one another. A system design optimized for expected performance may simultaneously have a non-negligible probability of single trajectory failure. A stopping time is a random variable defined on the probability space that captures the first instant at which the system trajectory exits the feasible operating region. Formally, the stopping time tau is the infimum of all times at which the state variable crosses the failure boundary. The system survives through time t if and only if the stopping time exceeds ti along that trajectory. Survival is therefore a trajectory-level event, not an expectation. The survival probability is the probability of this event under the law of the process. It is a quantity defined over the ensemble, but it measures a trajectory-level criterion. Three formally distinct system-level quantities arise from the same stochastic process model. The first is the expected state value at time t, an ensemble integral over all realizations. The second is the survival probability, the probability that a single trajectory remains within the feasible set beyond time t. The third is the almost sure limit, the value to which a single trajectory converges as time grows. None of these three quantities determines the others. Each requires separate computation and answers a distinct design question. The expected performance of a system and its survival probability encode conflicting architectural criteria. A system can have positive expected output, a favorable drift in the ensemble average, while simultaneously having a trajectory survival probability that declines towards zero. This is not a contradiction. It arises because the ensemble average is dominated by the outcomes of surviving trajectories, which may be atypically favorable. The failed trajectories are absorbed and removed from the ensemble, biasing the surviving average upward. An architecture evaluated only by expected performance will systematically understate the probability of individual system failure. The gambler's ruin problem provides a canonical formal proof of the divergence between expected value and survival. A random walk with positive expected increment still reaches the ruin boundary with probability 1 when the walk is unbounded below. This result holds rigorously under measure-theoretic probability and does not require utility theory. The implication for system architecture is direct. A system with a positive performance drift can still fail with certainty when the failure boundary is absorbing and the state space is not bounded away from it. Designing for positive drift is not equivalent to designing for survival. The branching process is a structural model in which expected growth and extinction probability are independent criteria. A supercritical branching process has expected offspring greater than 1. The population is expected to grow. Yet the extinction probability, the probability that a single lineage eventually reaches 0, may be strictly positive and can equal 1 in limiting cases. This demonstrates that ensemble-level performance guarantees do not translate into trajectory-level survival guarantees. System architectures that must guarantee operational continuity require explicit survival analysis, not merely favorable expected performance metrics.